Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine. So in today's lecture we shall consider about the use of common oxidizing agents which are used for the elimination of hydrogen. Right. So in today's lecture we shall study about the dehydrogenation reactions of alcohols, and for this purpose we shall study about the use of organic reagents. So in previous lecture you have studied about the dehydrogenation reactions of alcohols by use of inorganic reagents, but in today's lecture we shall study about the use of organic reagents for converting the alcohols into aldehyde and ketones. The key concepts of this lecture will be the dehydrogenation and the use of inorganic reagents for oxidation of primary, secondary and tertiary alcohols. So dehydrogenation reactions are the reactions that result in elimination of hydrogen from a molecule, right? So whenever there is elimination of two hydrogen atoms from a molecule, we say the reaction is dehydrogenation reactions, right? And dehydrogenation reactions are example of oxidation reaction, right? These are types of oxidation reactions because if you define the oxidation reactions, what are oxidation reactions? Oxidation reactions are the reactions that involve either the addition of oxygen or elimination of hydrogen, right? So in dehydrogenation, what we are eliminating the hydrogen. Therefore, the dehydrogenation reactions are a type of oxidation reactions. So there are different types of these dehydrogenation reactions that include aromatization. So when we have a six-membered ring and we convert this six-membered ring into benzene ring by elimination of three hydrogen molecules, this is an example of aromatization. So if we have alkanes and we remove the two hydrogens from alkanes, we get carbon-carbon double bonds, right? We have alcohols and we remove the two hydrogens from alcohol, we get aldehyde and ketones. And in case we have amines, we can carry out the dehydrogenation of amines to yield the nitriles. Also, we can convert the phenols or aromatic amines to quinones. We can oxidize the hydrazine, hydrozones and hydroxylamine into different functional groups. So in today's lecture we shall focus on the dehydrogenation of alcohols that will yield aldehyde and ketones, and in today's lecture we shall use the organic reagents. In the previous lecture we saw that when we use the inorganic reagents for the oxidation of alcohols, we get ketones from the secondary alcohol in good yields. However, when we use the primary alcohols, there is some problem of selectivity. So some of the inorganic reagents, they preferentially convert alcohols to carboxylic acid instead of converting them to aldehydes, right? So in organic reagents, the organic reagents are much more milder because the reactions of organic reagents are slower than the reactions of inorganic reagents. So we expect that organic reagents will be a bit more milder and they will be more selective for the oxidation of alcohols. So we'll see that how we can convert the alcohols to aldehyde and ketones by means of the organic reagents. So the oxidation of alcohols gives aldehyde and ketones. So if we have a primary alcohol, we get the aldehyde, and if we have a secondary alcohol, then we get the ketone. So overall, the oxidation reaction involves elimination of two hydrogen atoms. So one hydrogen is lost from the carbon and one hydrogen is lost from the oxygen. So as a result, we get a carbon-oxygen double bond, right? So since we are eliminating two hydrogen atoms, so this is a type of dehydrogenation reaction and it's also a type of oxidation reaction. So for example, we have a primary amine, right? Say here we have a primary amine because this carbon to which oxygen is attached, this carbon is further attached with just one carbon, right? So this is a primary alcohol, and in case of the dehydrogenation reaction, we are eliminating one hydrogen from oxygen and one hydrogen from this carbon. As a result, we'll get a carbon-carbon double bond here, right? So you can see if we have a carbon-carbon double bond here, so here we have a hydrogen and here we have a methyl group. So this is an aldehyde. So the oxidation of primary alcohols will yield aldehydes. Similarly, if we have a secondary alcohol, so why we are calling it a secondary alcohol? Because the carbon to which this oxygen is attached, this carbon is further attached to two carbons, right? So this is secondary alcohol. So we will remove one hydrogen from the oxygen and one hydrogen from the carbon. So we'll get a carbon-carbon double bond here. And to both sides of this carbonyl, we have methyl group. So this is a ketone. So the oxidation of secondary alcohols will yield ketones. Now we have tertiary alcohol, so we have an oxygen attached with a hydrogen. So here we have a hydrogen here, but there is no hydrogen on the carbon, right? So there is no hydrogen directly attached with this carbon, so we cannot carry out the elimination of two hydrogen atoms from this molecule. The tertiary alcohols do not undergo oxidation reaction, so they do not form aldehyde or ketones upon oxidation. So now let's consider different organic reagents which will be used for the oxidation of alcohols to aldehyde and ketones. So just remember, just for a reminder, always remember that the inorganic reagents are much more faster in their reaction and they are much more harsher in their reactions. The organic reagents, they work slowly, they have slower reaction rate as compared to the inorganic reagents, and they are much more selective. Right, so let's consider the first organic reagent which is used for the oxidation. So this reagent is known as the Swern's reagent, and oxidation is known as Swern's oxidation. Right, so this is a much more recent organic oxidizing reagent, and that involves the use of dimethyl sulfoxide. Right, so dimethyl sulfoxide is shortly known as DMSO, right? So this reagent is basically based on DMSO, right? And this reagent can oxidize the primary alcohols as well as secondary alcohols to aldehyde and ketones. So there is no conversion of primary alcohol to carboxylic acid, right? So this is the general reaction. Suppose we have an alcohol, so suppose we have a secondary alcohol here, and what we do in this reaction, we make use of oxalyl chloride. So one of the reagents is oxalyl chloride. The second major reagent is known as the DMSO, and third important reagent is a base. So you must have a tertiary base here, right? So there are the three reagents which are used in the Swern oxidation. One is the oxalyl chloride, second is the DMSO, third is a triethylamine here. So you can make use of any base here, but the base should be tertiary. So we need to have a bulky base. We need to have a tertiary base here, right? And by means of this reaction, what we do, we remove hydrogen from this oxygen and hydrogen from this carbon, so we'll get a carbon-carbon double bond here, right? So let's consider about the mechanism. So mechanism is a very complex one for this reaction. So however, if we have to summarize that, the reaction involves firstly the conversion of these alcohols into the sulfoxonium ion by reaction of alcohol with DMSO and oxalyl chloride, right? So here we have sulfoxonium ion, right? So there's sulf because that's sulfur, and oxo means that that's attached with an oxygen, and onium means there is a positive charge on sulfur, right? So always remember that whenever you have some name ending with em, right, or some name which is ending with onium, right, so em or onium, that indicates that that atom has a positive charge. So if we have sulfoxonium, mean there is sulfur that's attached with oxygen, and sulfur is having a positive charge. Similarly, you have bromonium, right? So onium or em, whenever there is a name, always remember that that atom has a positive charge on it. So this sulfoxonium ion is formed as an intermediate in this reaction, and the sulfoxonium is formed when the alcohol reacts with dimethyl sulfoxide and oxalyl chloride. So this is the intermediate of this reaction. So this sulfoxonium ion decomposes to form this dimethyl sulfide, right? So what we'll get a dimethyl sulfide. So this molecule will be eliminated here. Then we will get the aldehyde and ketone as our desired product, and this also reaction involves the loss of carbon dioxide. We can see here there's carbon dioxide from here, and this reaction also involves the loss of carbon monoxide, and this intermediate also will involve loss of Cl that will form ultimately the HCl, right? So this is the reaction. Just see what about the mechanism, how it happens. So this is the mechanism for Swern's oxidation. So we have a dimethyl sulfoxide here. So this is the structure of DMSO. So dimethyl, so we have two methyls, attached with its sulfoxide, because sulfur is having a double bond with oxygen here, right? So this is dimethyl sulfoxide here, and this is actually can be represented in the form of resonance like that. So we know that if we have opposite charges on the adjacent atoms, like here, so we can see that this is equivalent to a double bond here, right? So if you have opposite charges on the adjacent atom, that's equivalent to a double bond here. So the reason for showing this is that this oxygen is rich and the sulfur is deficient. So in the first step, this canonical form of the dimethyl sulfoxide that will attack on this oxalyl chloride. So this is oxalyl chloride here, right? So it's basically that's chloride of oxalic acid, right? So if we attach two oxygens, hydroxyl group here, so that will be oxalic acid, and this is oxalyl chloride. So what happens in the first step, this oxygen of the DMSO that will attack as a nucleophile on this carbon, right? So when this nucleophile attacks on this carbon, what happens that this chlorine atom will leave, right? So this chlorine will leave in order to satisfy the valency of this carbonyl. So what we'll get, we have got a oxygen bonded with this carbonyl of the oxalic acid, oxalyl chloride, and we have got sulfur, which is positively charged. So this is the sulfoxonium ion, and this is the intermediate of this reaction, right? So what happens that this chlorine, right, this chlorine will act, and this chlorine will attack on the sulfur, right? So now this chlorine is electronically rich, so that will attack as a nucleophile, and that will attack on this sulfur, right? So sulfur is positively charged. So what happens that this bond will cleave in the favor of carbon and oxygen, right? So this sulfur bonded with chlorine, that will again get detached from here, right? And we will get a carbon oxygen double bond here, right? So you know that this carbon is having 5 valency, which is not possible. So what happens, so this bond will shift towards this carbonyl group, and this chlorine will leave. So we have eliminated a molecule of carbon dioxide from here, we have eliminated a molecule of carbon monoxide from here as well, and also we have eliminated a chlorine atom and the form of chloride ion here as well. So now this is another intermediate of this reaction, right? This is again an onium ion, sulfonium ion, right? That's not sulfoxonium ion because there's no oxygen attached with sulfur, right? So this sulfonium ion is the second intermediate of this reaction, and it is this intermediate with which our alcohol will react, right? So what happens that our alcohol will attack as a nucleophile on this sulfur. And why it's attacking on the sulfur? Because sulfur is having 3 bonds and it's positively charged, right? So oxygen is a good nucleophile that will attack the nucleophile on the sulfur, and we'll get a oxygen sulfur bond here. Alright, so we'll be getting an oxygen sulfur bond here. So once the bond is formed with sulfur, the positive charge of sulfur will be ended up, but we'll get a positive charge on this oxygen because this oxygen is currently having 3 bonds, right? It's bonded with carbon, it's bonded now with sulfur, it's also bonded with hydrogen. So at this step, this chloride ion will come, and this chloride ion will act as a base, and this chloride ion will pick up this hydrogen, right? So this will pick up this hydrogen so that the positive charge on oxygen will be neutralized, so we'll get an HCl here, right? So this HCl is eliminating here. So what we get is that we get this molecule here. So there's an ionic bond between sulfur and chlorine, so this bond is still present, like here, right? So what happens next is that now the base will come and the base will pick up the proton, right? The base will not pick up the proton of this alcohol from here. Instead, the base will pick up the proton of this methyl of sulfur, right? So here we have a proton here. So what will the base will do? So base will pick up this proton, right? So when the base will pick up this proton, we'll get a carbon which will be negatively charged here, right? So we got a negative charge on this carbon of the methyl group. So now this negatively charged carbon that will act as a base and will pick up a proton from this alcohol part, right? So what happens that this negatively charged carbon will act as a base and will pick up this proton. So this proton will lose its electrons here, so we are getting a carbon oxygen double bond, and this bond between oxygen and sulfur will cleave, so that sulfur becomes neutral, right? So here we have got a dimethyl sulfide group. So this was the dimethyl sulfide group here, right? So we have got dimethyl sulfide group, and we have eliminated this hydrogen, right? And we have got a carbon oxygen double bond here. So that's the mechanism of Swern's oxidation, right? So in the first step, what we do is that firstly, dimethyl sulfoxide will be converted into its other canonical form. So in the other canonical form, which is charged, the oxygen with the negative charge will attack on this oxalyl chloride and will get a chlorine eliminated from here, right? In the next step, what happens that this chlorine, it is having an ionic interaction with the sulfur, but that will attack and form a covalent bond with the sulfur, right? And at the same step, the oxygen and sulfur bond will break and will eliminate a carbon monoxide from here and a carbon dioxide from here, right? And we'll get a second intermediate, which is sulfonium ion. And this second intermediate our alcohol will react with, right? So the oxygen of this alcohol will attack as a nucleophile on the sulfur, and what happens that we will have an elimination of HCl, right? So this is another intermediate that's formed in this reaction, right? So the base, which was tertiary base, which has to be a tertiary base, will be used here. This tertiary base will pick up a proton for the methyl of hydrogen of this methyl, and this negatively charged carbon will act as a base and will pick up this proton, right? And I'll get a carbon oxygen double bond here, and this bond to sulfur will be cleaved. So ultimately we'll get an aldehyde or ketone, and we'll also get dimethyl sulfide here as a side product, right? And if you just see that this reaction is occurring at minus 78 degrees C, means we don't have to heat the reaction. So the reaction works very well at very, very low temperatures. Now we have examples of Swern's oxidation. Suppose we have an alcohol, and you can see this is a secondary alcohol because this carbon is bonded with two carbons, right? So we'll get a carbon-carbon double bond by elimination of hydrogen from this carbon and hydrogen from this oxygen, right? So this is dimethyl sulfoxide, DMSO, and this is the second reagent, which is oxalyl chloride, and here we have a tertiary base, which is triethylamine, and the solvent normally we use is dichloromethane, because all of these reagents are very, very soluble in dichloromethane. So ultimately we will get a ketone from secondary alcohol. Also we will get the dimethyl sulfide, and we'll get carbon monoxide, carbon dioxide, 2 molecules of HCl as a part of this reaction, right? So another example, so here we have cyclopentanol, and this is again a secondary alcohol, and when we carry out the reaction, so we need to have a dimethyl sulfoxide, we need to have an oxalyl chloride, and we need to have a tertiary base, and the reaction conditions should be low, so ideally we use minus 78 degrees C. So this reaction is specifically working at minus 60 degrees C. So what we'll get a carbon oxygen double bond here. So this is a way in which we can convert cyclopentanol into cyclopentanone, and you can see the yield. So yield is quite high, it's 90% yield for this reaction, right? So that's all about the Swern's oxidation. The next reagent which is normally used for the oxidations is Oppenauer oxidation, right? It's a gentle method, it's also a selective method, but this method is useful for oxidizing secondary alcohols, and the oxidation of secondary alcohols will convert into ketones. Right, that's a limitation, that we can convert the secondary alcohols into ketones, right? However, this is milder, that's a selective reagent, so if you have a substrate that has a lot of functional groups, so you can use Oppenauer's oxidation, because Oppenauer oxidation does not affect other functional groups. It will just convert this secondary alcohol into ketone nicely and cleanly. So the reagents which we are using for this reaction should be a proton source. So normally we use an acetone there should be methyl ketone here. So in this case we are using acetone. So acetone is a reactant in this reaction. Also we have an aluminum with 3 isopropoxy groups attached here, right? So this is the second reagent, and this reaction involves use of heat, right? So the reactions works well when we are using excess of acetone. And why we are using acetone? Because the reaction is sort of equilibrium process, and we want to shift the equilibrium towards the product side, so we need to have a reactant which is in excess, right? So what we use the acetone in excess. So having a reactant in excess will move the reaction towards the forward side. So the main step of this reaction is the transfer of hydride from alcohol to acetone, right? So in this reaction the alcohol will lose a hydrogen in the form of hydride, and this hydride will be accepted by this acetone, right? So let's have a look at the mechanism of this reaction. So in the first step, what happens that we have our secondary alcohol. So this alcohol oxygen of the alcohol will act as a nucleophile, and it will attack on this aluminium, because aluminium, you know, is a member of group 3 and it's electron deficient, right? So what happens that since that's 22 electrons, so this is a type of ligand exchange. So the attack of this oxygen on the aluminium will result in loss of one isopropoxy group. So this isopropoxy group will be lost, and we'll get a bond of this oxygen with this aluminum here, right? So now this oxygen is having 3 bonds. So what happens, the isopropoxy group that was lost will act as a base and will pick up this proton here, right? So by means of picking up this proton, we can neutralize this positive charge on the oxygen. So we have got rid of this positive charge here. So you can see this aluminium has 2 isopropoxy group attached, and the third is our alcohol, right? So we have got this isopropoxy group here, isopropanol here from this isopropoxy group. So this reaction, you can see that reaction is reversible. So in the next step, what happens, the acetone, which was the second reactant, this acetone acts as a nucleophile, and that will attack on this aluminum, and it will form a 6-membered transition state, right? And the 6-member transition state is very stable because it's forming a chair-like conformation. So just for explaining how it's forming a chair-like conformation. So this is our alcoholic part. So you can see the R2 and R1 groups, right? This is the oxygen of our alcohol, and this is the hydrogen of our alcohol. So we have not shown hydrogen here, but there is a hydrogen which is actually here, right? So this hydrogen, this is the hydrogen of this alcohol. You can see this oxygen of alcohol is bonded with aluminum, and aluminum has 2 isopropoxy groups attached here, right? And now this acetone has attacked on this aluminum. So this acetone is forming a bond with aluminum right here, and this is the acetone. You can see that this bielectronic density is shifting toward aluminum. So this bielectronic density is becoming finished, and there is a bond that's being formed between the aluminum, right? So what happens that this hydrogen of our alcohol that is showing attraction to this carbon of the acetone, right? Why is that showing this attraction? Because this carbon is becoming deficient. Bielectronic density is ending from this carbon, because this bielectronic density is forming a bond between oxygen and aluminum, right? So this carbon is getting a full positive charge, and this hydrogen of this alcohol is showing affinity for this hydrogen, right? What happens that this hydrogen will actually migrate to this carbon, and when it migrates, it will take the electron with it, right? So this hydrogen will attack on this carbon, and this hydrogen will transfer as hydride ion, H negative ion, right? So what happens, you can see like that. So this is our acetone. You can see this acetone is forming a coordinate covalent bond with the aluminum. As a result of this coordinate covalent bond, this carbon is becoming positively charged here, right? So this is our alcohol, and this is hydrogen of alcohol. So this hydrogen is migrating to this carbon, right? And when it's migrating, it's taking an electron with it. So this is the hydride shift. So next what happens that this bond will shift towards this aluminum. So we'll get a bond of aluminum with oxygen here, and this bond of aluminum and oxygen will be cleaved. like that, right? So we'll get a carbon oxygen double bond here, and we'll have a we have a ketone that was acetone, and the hydrogen will be shifted to this acetone, and now at present this acetone is bonded with aluminum, and we have got our ketone free, right? And what happens next? In the next step, we add water, and when we add water, so this bond between the aluminum and oxygen is cleaved, and we get an isopropanol with this reaction. So you can see this reaction is very reversible, right? So how we can shift the reaction to the product side? So by means of simple Le Chatelier principle, we know that if we take one of the reagents in excess, so the reagent, if we are using in excess, the excess of the reagent will ensure that reaction moves forward directions. That's why we are using this acetone in excess, right? So this is the mechanism for this reaction, right? The limitation of the Oppenauer's oxidation is that we can only convert the secondary alcohols to ketones. So this reaction is not applicable for the primary alcohols. However, the advantage of this reaction is that if you have very complicated structures, if you have a structure with a lot of functional groups, then you can use this Oppenauer's oxidation, and it does not affect any other functional group except the secondary alcohol. So for example, consider the structure of codeine. So this is all structure of codeine. You can see how much complicated it is. But when we use this ketone and aluminum isoperoxide here, so what we get simply the ketone here, right? So nothing is disturbed. Stereochemistry of everything remains the same. Just we convert this secondary alcohol into a ketone. So here we have another example. So here we have this system, and you can see that we have double bonds here. We have this oxygen here, hydroxyl here is part of 6-membered ring, right? So what happens that when we use this condition, so we must have some aluminum, right? So this is aluminum which is triply bonded here, right? So we need to have triply bonded aluminum. So it doesn't necessarily means you must only have this isopropoxy groups here, right? So the important thing should be that aluminum must be triply bonded, and the ligands must be able to be exchanged. So right, so we can break the bond of this oxygen with aluminum. So also we can break the bond of the nitrogen with aluminum as well. So what happens that in this reaction, we are using a carbonyl group as another reactant. So we can have any ketone, we can also have an aldehyde here, right? So we are using this tertiary butanaldehyde here because this carbonyl has to accept the hydride, right? So we cannot make use of any other functional group. So anything that can easily accept this hydride will act as a second reagent, right? So under these conditions, what we are getting simply the oxidation of the secondary alcohol into this ketone here, right? So the third reagent which is normally used for the oxidation of alcohols is the Dess-Martin periodinane. It's commonly known as DMP. It's a chemical reagent that's used to oxidize both primary alcohols and secondary alcohols to aldehyde and ketones. So very selective, very efficient, but it has a very great problem. It's very expensive and it's very explosive, right? So because it's very expensive and it's very explosive, it cannot be used on an industrial scale or other than these limitations. That's perfect reagent for oxidation of primary alcohols and secondary alcohols. So this is the structure of Dess-Martin periodinane, right? So you can see here, this is an iodine, and with this iodine we have 3 acetoxy groups attached. So this is an acetyl group, and acetyl is attached to an oxygen. So we are saying that as acetoxy, right? So these 3 acetoxy groups are attached with this system, right? This is the structure of Dess-Martin periodinane, right? So what's the important thing in this reaction? That these acetoxy groups are very easily replaced. So in the Dess-Martin periodinane, why that reagent is efficient? Reagent is efficient because the ligands which are attached to it, these acetoxy groups, these can easily be replaced. That's why that's very fast and that's very selective reagent. So Dess-Martin periodinane has several advantages over chromium and DMSO based oxidants, right? So among chromium reagents we have studied in the inorganic section, and the DMSO based oxidant is basically Swern oxidation. right? And the advantages include it requires milder conditions, right? In Swern's oxidation, you knew that the reaction has to be carried out at very low temperature, so you have to maintain a temperature of minus 78 degrees C or minus 60 degrees C, but DMP reactions work at room temperature. They also work at neutral conditions, so you don't need to make the reaction acidified or basified. Also, the reaction is very fast, takes very short time, gives very high yield. The reaction work are very simple, and the yield are very high with high chemoselectivity. And if you have sensitive functional groups, so this DMP does not affect the sensitive functional groups as well. It has a long shelf life, very highly stable molecule. However, the disadvantage that was told you that it's very expensive and it's very explosive reagent. So let's consider the general reaction. So this is our alcohol. So this can be alcohol, that can be primary alcohol or secondary alcohol, and this is our DMP. Right, so DMP cleanly converts primary alcohol or secondary alcohol into aldehyde or ketone. Right, so that's special reagent, and it's very normally used when your substrate is very complex, and if your substrate is sensitive and has large number of alcohols. Right, so if you have substrate is very complex, it's very sensitive, has a large number of sensitive groups, and it has a number of alcoholic groups, then you can use DMP as a reagent, right? So why DMP is selective towards the alcohols is that because it allows rapid exchange of ligand when our alcohol attacks on it, right? So just see the mechanism of here. So this is our DMP. What happens in the first step? So in the first step, our alcohol will attack as a nucleophile, and that will attack on this iodine, right? So when it attacks on iodine, so this acytoxic group will be eliminated. See how readily there is a ligand exchange. So we are exchanging this acytoxic group with our alcohol, right? So this is very rapid ligand exchange, and because of that reason, the reaction is very fast and the reaction is very selective. So once our alcohol has reacted, next step is that the acytoxic group that was lost in the first step, that acytoxic group acts as a base, and that will pick up proton from this alcohol. Right, you can see this is an acytoxic group that was lost from the last step, and this acytoxic group is that's picking up the proton of this alcohol, and this proton is shifting its electrons between carbon and oxygen, and what happens that this oxygen and iodine bond is being broken, right? And when this bond is being broken, this acytoxic group is being eliminated, right? So just remember that iodine is a halogen, and halogen have stable valencies of 1, 3, 5, and 7, right? So in case of DMP, this iodine is having oxidation state of 5, that's stable, and here the oxidation state of this iodine is 3, because iodine is having 3 oxidation state here, right? So iodine cannot have oxidation state of 5, 6, it cannot have an oxidation state of 2, it cannot have oxidation state of 4, right? The oxidation state should always be 1, 3, 5, 7. With these oxidation state, iodine is neutral. So in iodine, the oxidation state of iodine is 3. So what we have got our ketone or aldehyde, right? We have got the acetic acid because of that acytoxic group. So acytoxic group, when it picks up a proton, that gets converted into this carboxylic acid. This is an acetic acid here, right? So that's the mechanism for DMP. So you can easily see that here the intermediate is diacetoxy-alkoxy-periodinane. So why we are saying it as diacetoxy-alkoxy? Because iodine has 2 acytoxy groups attached here and 1 alkoxy, because there is an alcohol, right? So when alcohol is attached to something, we say it as alkoxy, right? Alkyl group attached with the oxygen, so that's an alkoxy group, and these are acytoxy groups, right? So when we have monohydric alcohol and we react with the DMP, the intermediate is diacetoxy-alkoxy-periodinane. Now, if our reagent is a diol or has more than one alcohol, then the mechanism is same, but in this case the intermediate is been different, right? So what happens in this case, we have two hydroxy groups here. So both of these hydroxy groups will result in replacement of two acidoxy groups here, right? So this hydroxy group will result in elimination of this acidoxy group. Similarly, this hydroxyl group will result in loss of this acidoxy group, right? So two acidoxy group will be lost, and these two hydroxyl groups will get bonded with this iodine. Alright, so oxidation state of iodine was 5, still the oxidation state of iodine is 5 as well. So next step, what happens, the this acidoxy group that was lost in the previous step, so one of these acidoxy will act as a base and will pick up a proton, and what happens, you can see here, right? So this bond between carbon and oxygen is becoming double, so we are getting carbon-carbon double bond here, and the oxygen iodine bond is being cleaved here. Next, this bond of iodine with oxygen will also be cleaved, so we will get this product. So we'll get a carbonyl group here, and this hydroxy group will be retained, right? So in this case, we can get alpha hydroxy ketones or alpha hydroxy aldehydes depending on the nature of this R group here, right? So this is the difference in the intermediates. In case if you're using monohydric alcohols, the intermediate was diacetoxyalkoxy periodinane, but when you are using dihydric alcohols, then in that case the intermediate is different. The intermediate is acetoxy because we have one acetoxy. So the intermediate is acetoxy dialkoxy periodinane, right? And the reaction is very fast, the reaction is very clean, but the problem, as I've mentioned, that DMP is very expensive, and the problem with DMP is that it's very expensive as well as explosive, so it cannot be used on larger scale, it cannot be used on industrial level. So here we have some examples of DMP. So simple, so we have an alcohol, right? This is a primary alcohol with DMP, so we also use dichloromethane as solvent, and under these conditions this alcohol is being converted into aldehyde. So here we have a conjugated system, right? And here we have a primary alcohol. So the DMP does not affect all of these double bonds, so nothing is changed except we just oxidize this alcohol into aldehyde. Again, we have a very complicated system. So here we have an acetal linkage, we have this ether linkage, and we have an hydroxy group. So our DMP will only convert this alcohol into the carbonyl system, nothing will change. Again, a complicated system. So here we have two systems. So we have tertiary alcohol, and here we have secondary alcohol. So in the lecture very start, we mentioned that tertiary alcohols cannot be oxidized because this carbon has no hydrogen to be eliminated. So tertiary alcohol will remain like that, and just we will oxidize the secondary alcohol. So this is the effectiveness of desmortin periodinane. That's very selective, that's very fast, and that yields the product in a very selective and efficient manner. It's just like we can have a summary of the organic and inorganic reagents combined. So if we have a starting material as primary alcohol, then we must have some weak oxidants. The oxidizing reagents must be weaker, they must be milder. So if you are to convert primary alcohol into aldehyde, you must use PCC because it's selective and it's very milder, or you may use DMP, or you may use Swern oxidation, right? But if you use strong oxidizing agents like MnO4, or you use the potassium dichromate or the chromic acid, in that case you cannot get aldehyde, instead you get the carboxylic acid as the product. With secondary alcohol, you can make use of any of the oxidizing agent, whether that's weak or whether that's strong. So reaction works well in those conditions, and from secondary alcohol we get the ketone in each case. While in case of tertiary alcohol, since there is no hydrogen attached to this carbon, so there is no reaction with tertiary alcohols, whether you are using strong oxidizing agent or you are using weak oxidizing agent, right? So that's all for today's lecture. I hope you have understood it well. Thank you.